Well, thanks a lot for the introduction and for having me for this VSA talk seminar. So I will present a work which we already have presented at date 2020. So it's about compressing the subject-specific brain-computer interface models using the superposition in hyperdimensional space. But first of all, let's have a look what the brain-computer interface is. A brain-computer interface builds a communication channel between the human brain and an external device, only based on the human's thinking. However, what we require is that the human thinks about specific tasks. So for example, about the movement of a body part. And this is called motor-imagery. So as soon as a person is thinking, for example, about the left hand, we record the brain activity with electroencephalography or EEG. And then we can send a part of this EEG data, for example, to an external cloud or a server, which can do the classification for us. Hopefully, it will then do the right classification and predict the left hand and can send a command, for example, to a wheelchair for steering the wheelchair or a paraplegic user. However, doing this processing on the cloud comes also with some limitations, mostly because we need to send the data to the cloud. This requires large bandwidth, a lot of power, and also comes with some latency to send it to the cloud and then back. This is especially problematic for time-critical applications, as well as some privacy issues. So we may not want to share our raw EEG data with third parties. So what we propose here instead is to have a device which is called embedded MI-BCI, where we do the processing and the classification directly on the device near the sensors. This solves most of our problems, meaning we can reduce the required bandwidth because we can send the commands directly to the wheelchair. We can therefore also reduce the power consumption, the latency, and also hopefully we can increase the protection of our user data as we don't need to share the raw EEG data with third parties. However, today's MI-BCIs still come with a lot of challenges, and this is mostly because the EEG data is very subject specific. So meaning it varies a lot between different subjects. Therefore, we need to have a separate model per subject. And to have these models, we first need a separate training or calibration measurement for every subject. And on this data, we can then train the corresponding model. When we then want to have a practically usable MI-BCI on an embedded device, we need the capability to store multiple of these models on device. This gives us the capability to operate it for different subjects. So maybe when I have, for example, 8 friends and I want to have a BCI for all of my 8 friends, I need to be able to store it for the 8 friends and myself. Moreover, when having multiple models directly on my embedded MI-BCI, I have the ability to reduce the calibration time. So maybe I get a new 9th friend, which also wants to use my MI-BCI, and we simply do together a short or small amount of training calibration measurements. And based on that, we can, for example, select the best fitting model and apply that model for the new 9th friend. However, of course, what we will end up is we run into capacity issues in terms of the storage capacity on our embedded device. So we cannot store an infinite number of models on our embedded MI-BCI. And here in this study, we look at how we can reduce the memory footprint of this multiple of the subject-specific MI-BCIs. So we have couple of options at hand. So one option would be to just use one global model for all of the subjects. Another way is to reduce the precision of our model weights. So we can, for example, use 8-bit fixed point instead of 32-bit floating point weights. However, both either using the global model or doing weight quantization yields or has shown to yield lower classification accuracy. What we show in this work is how to compress this multiple of the subject-specific models using the superposition in hyperdimensional space. And with that, we were able to compress our model by 3 times at even higher accuracy than the non-compressed models. So let's have just a quick look at with what data we are working. So we're working with the BCI competition 4-A dataset. This one is publicly available. And this dataset has 9 subjects, and every subject participated in 2 sessions. So one session is the training set on the first day, and then we have a second session, which is the test set, which was recorded on the second day. Each session consists of recordings of 288 trials, and each trial includes one of the 4 motor-imagery tasks, which is movement of the left hand, the right hand, both feet or tongue. The data was acquired with 22 EEG channels and sampled with 250 Hertz. So if we look at this case study, we need basically 9 subject-specific models to store on our embedded MI-BCI. So one model we could have a look at is the shallow ConvNet. This is a really lightweight convolutional neural network with basically 3 layers. So we have the temporal convolution, the spatial convolution, and in the end, the fully connected layer. Overall, this model has 47K weights, whereas we're already seeing that the majority of the weights is in the spatial convolution, as well as in the fully connected layer for the classification. So these are kind of the layers which we are at first really interested to compress. When we apply this with subject-specific training and testing, we achieve a classification accuracy of 73.59%. So I will now introduce the key value binding, superposition, and approximate retrieval in hyperdimensional space. The original idea to use this superposition for compressing many models into one was initially introduced by Zheng et al. And there it was mostly applied on vision data. And here in this case, we applied, as I already introduced, on biosignal data. Moreover, we use a different binding and retrieval operations. So let's say we start with a set of value vectors, which are in the d-dimensional real valued space. These 3 value vectors can be of any correlation, or they can have any relation to each other. For example, they can also be orthogonal or even collinear. And what we then do is we bind each of these value vector with a specific key vector. And when we choose the right key vectors, we can build quasi-orthogonal key value pairs. If we then want to retrieve one or all of these key vectors, we can apply the approximate inverse binding operation, which gives us the estimation of the value vector W1 to W3. So as we were able to orthogonalize this value vector using the key value binding, we can also superimpose those. So this is shown here. So we first built the key value pair for every value vector. Here for the binding, we use the circular convolution, and as key, we use d-dimensional vectors with elements which are drawn from an IID Gaussian random variable. The variance is set to 1/d to keep the unit norm. Then we superimpose all of these key value pairs, and for estimating or using one of this value vector, we can do the unbinding operation, which is approximate in this case, on this superposition. And in our case, the unbinding is simply circular correlation. So you might guess we are using here the holographic reduced representation. So what we get when we do the unbinding on this superposition is eventually an estimation of the actual value vector we want to have, and also some terms which come from the neighboring value vectors. However, with high probabilities, those tend to zero. So in the end, we have the value vector plus a certain noise term. Most importantly here, we don't do any associative cleanup. So that's actually the estimation we will further work with. We don't do any cleanup. This would defeat any purpose of doing the compression in this case. So we now link this key value binding to the key weight binding for compressing the weights of this convolutional neural network I've shown you before. So let's say we have all the weights in the model, and we want to just compress the weights of it. So we extract these d weights and put them into a d-dimensional vector W1. And then at the same time, we also generate a key vector K1. And for that, we seed the random number generator with a subject-specific key value. And this key value can be just a random seed, can be, for example, 32 bits. So we can generate this key vector K1 on the fly, do the binding, which gives us the key value pair or key vector pair V1. We still have some of the weights which we don't use for the superposition. Those we just keep aside and store them separately. So now we do this operation not only for, let's say, subject 1, but all the subjects we want to do a compression. So for every subject we have use a subject-specific random seed to generate our key vector, and then we can generate these key value pairs, which we in the end superimpose. So overall, this gives us then this superposition S, as well as all the non-compressible weights on the side. Overall, we can then, with that, we can basically compress all the subject-specific models into one model, and with compression rate, which depends on the number of subjects, as well as the ratio between the dimension of our vectors, which are the number of compressible weights, and the overall model size. So if we want to operate now the model for one subject, so in this case it's for subject 1, we take again the superposition S, generate on the fly on the device our key vector K1, and estimate the value vector or the weight vector W1 and put it into our model. At the same time, we also take again our non-compressible weights and feed them into the model. So if we do this operation, as I explained you, on the fully connected layer, so our compressible weights are taken from the classification layer, meaning the fully connected layer, and we achieve a compression rate of 1.26. However, we see a large accuracy degradation due to this superposition and retrieval in the hyperdimensional space. This is mostly attributed to the noise we introduce by this approximate retrieval. So I will now show measures how we can improve the accuracy using iterative retraining. So we want to train the model in a way that it gets robust towards the noise we introduce when doing the approximate retrieval in the hyperdimensional superposition. So let's say we have already given a pre-trained model and we stored them in the superposition S, and we have at the same time also our non-compressible weights. Now we retrieve the weights for subject 1 and do a couple of retraining iterations or retraining epochs. So let's say we do 5 epochs and update the model S with the new weights both from the superposition as well as from the non-compressible weights. And we play this game not only for subject 1, but of course for all of the subjects, and this for multiple retraining iterations. So in this slide, we see the training misclassification rate for subject 1 over multiple of these training iterations. So at the beginning of a retraining iteration, we retrieve our weights and store them into the model. If we test our model at that point, we see that we have a poor classification or a high misclassification rate. However, as we start to do some retraining epochs, we see that we can reduce the misclassification by quite an amount of percentage points. And at the end, after we finished with the retraining of that subject in this retraining iteration, we update our compressed representation as well as the non-compressible weights. Now, after this, we do the same procedure for all the other subjects. And as soon as we are done with the other subject, we retrieve again the model to do the retraining. So, and then we see that the misclassification rate goes up again. So what's really essential in this illustration is that what we actually care about is what is the misclassification rate directly after the retrieval. And this continuously goes down as we do this retraining and this iterative retraining. So we are able that our CNN model gets basically used to the noise which is introduced to this approximate retrieval of the weights. So we did take a couple of measures to introduce and improve this retraining, which is one of these things is we do randomized subject ordering. So we're not only just training subject 1 after 2 and so on, but we're always shuffling the order after every retraining iteration. Moreover, we conducted a fine-grained grid search over different hyperparameter selection, and this gave us a huge gain in classification accuracy. For that, we first split our training set into training and validation set and found the best hyperparameters in terms of batch size, number of epochs per iteration, the learning rate, and also the number of retraining iterations overall. So here in this plot, we see the misclassification for subject 1 and on average over all the subjects on the training set in green and on the validation set in blue. We also show the validation misclassification when doing no compression at all. So we see that the training misclassification goes down very, very rapidly. At the same time, we also see that the validation misclassification also converges towards the initial misclassification when doing no compression for subject 1 as also for on average. So it tends to go towards the misclassification rate we had before. Just remember that the results I'm showing here are on the validation set of which is part of the training set. What I will show you next will be on the test set, and this will be different numbers. So here we see again the shuffle net and the classification accuracy when doing no compression at all. So as we already have seen before, if we do the superposition of the fully connected layer and doing no retraining at all, we get this huge accuracy loss of around 20% compared to the non-compressed model. However, if we do this iterative retraining I just explained, we even can achieve a higher accuracy of 75.14% at a compression rate of 1.26. If we instead compress the spatial convolution, which is the biggest layer in this network, and we achieve a higher compression rate of 2.95, and still we are able to achieve high classification accuracy, even higher than the non-compressed model. If we compress both the spatial and the fully connected layer, we see accuracy degradation. This can be partly attributed to the capacity limit of this shallow ConvNet. In this case, to investigate that further, we had a look at an even smaller network, which is called EGNet. EGNet mostly uses stepwise and separable convolution instead of this big spatial convolution block. And with that, we are able to reduce the size, that it is able to reduce the size of the network by more than an order of magnitude. So overall, this network has 2.4K, where we see again that the majority of the weights lies in the fully connected layer. So if we apply this EGNet on the BCI competition for 2A, we see a compression and a classification accuracy of 72.32%. And if we compress the fully connected layer, we again achieve a higher accuracy than the non-compressed network at the compression rate of 1.9. So this slide summarizes all the results. So we see on the y-axis again the accuracy on the BCI competition for 2A, and on the x-axis the number of parameters for storing all 9 models on an embedded device, for example. And as we have seen before, for the shallow ConvNet, we are able to reduce the number of trainable parameters by 3 time around and achieve higher accuracy. The same holds also for the smaller shallow smaller EGNet, which we can compress by 1.9 times at 2.4% higher accuracy. So to conclude, here we presented how to apply hyperdimensional superposition to compress already compact MI-BCI models. What we mostly need is the iterative retraining to make the model, the CNN, robust towards the introduced noise which we see from the approximate retrieval. We have shown that we can compress 2 already lightweight CNNs, namely the shallow ConvNet and the EGNet by 3 to 1.9 times, both at higher accuracy. So what's next? So we've seen that we are indeed able to compress these networks, but what we are eventually, of course, interested is when this will degrade. So we will try to superimpose more models, and for that we can use larger data sets which are actually available. So there, for example, is the PhysioNet with more than 100 subjects, which we can use for this superposition hyperdimensional space. If you are interested in this work, you can look at the paper which we presented at date, and there is also the code which is available on GitHub and can be used freely. And with that, I'm open for any question.
Michael, thank you very much for your excellent talk. So now I open the floor for questions. So please unmute yourself and speak out.
Michael, it's Dennis speaking here. Why do you think the superimposed version provides a high accuracy? Because it's not completely intuitive, right? Because in principle, we orthogonalize different networks. So they live in different, let's say, corners of the space, but somehow still the fact that we combine them together allows us to reach high accuracy. Do you have any insight on that?
Well, what we also could have like we look at it is that with our iterative retraining, we always like insert some kind of noise in our network. So we force the network to be robust against this noise, and maybe we can also look at that as a sort of regularization, right?
Right. Yeah, indeed. It's like could
And
be a regularization.
yeah, and we also we really we took the training of these original networks, the EGNet and the shallow ConvNet. We took it as it was presented in the corresponding works, And we really optimized this iterative retraining when doing this fine-grained grid search for finding the right retraining hyperparameters. So we also do a couple of iteration, like retraining iterations more than in the original network. This is mostly attributed also because the retraining is more difficult than training the original networks. But maybe with the introduction of this kind of noise into the weight, we might make it more robust, because the amount of data we have available per subject is really small and mainly limits the performance of these networks. That's why we also still work in that tiny networks, let's say, and don't make it too bigger networks because training is so hard. So maybe with this new retraining iteration, where we take multiple models more or less into one, we can introduce some regularization.
I see. Thanks.
Any more questions? Maybe I have a question of my own. Just to increase my understanding, so this retraining process, do I understand it correctly that you kind of you redo the superposition? So you kind of update the superposition for every retraining epoch?
Yes, we kind of put this superposition into the training loop, right? So we train every subject separately. And so, yeah, basically, we even start with a non-trained network at all. So we start with a random network. We retrain that given model, let's say for subject 1, and then we update our superposition, meaning that we basically subtract the old one, right, and add the new one to it of subject 1. And then we do this for all the subjects. So one retraining iteration for subject 1 would be load the data, retrieve the weights, then we retrain it for about 5 epochs only, and then we already store it again into our superposition.
Okay, right. And that's what you say, is that the accuracy will be higher on average. I mean, for all the subjects, not for the...
Yes, what I'm showing is average accuracies, yeah.
Okay, interesting. More questions to Michael? Well, as usually, I remind you about our mailing list. So if you make up your mind and come up with new questions, so please communicate it to the community and to Michael. But then it looks like we approaching the end of today's webinar. So what is left to say is probably Merry Christmas to everybody. So this was the last webinar before for 2020. As I said previously, so please volunteer to give talks in 2021 or give suggestions of whom you want to hear. Send messages to me. And the last thing I want to remind you is that the next webinar is scheduled on 11th of January with the early start, so at 18 Central European time. But it will be recorded as usually. I will come back to you with the agenda for that seminar in a separate email. But that's it for today. So thank you very much for attending this webinar. And it was very great to see you all here. So Merry Christmas and Happy New Year, everybody. Stay safe.
Merry Christmas.
Yeah. Bye.
Thank you. Bye.